An EC 250.122 establishes the minimum size of the equipment grounding conductor, or EGC, based on the rated ampacity of the overcurrent protection device, or OCT, supplying the circuit. Wire sizing may need to be increased for voltage drop considerations to maintain acceptable voltage levels at the load. The dominant rule depends on the specific scenario. In the first scenario, if the OCT and current remain unchanged, then 250.122 governs the EGC size. The EGC size already meets the minimum requirement based on the OCT rating, so it does not need to increase for voltage drop purposes. In the second scenario, if the OCT or the circuit current increases, then 250.122 becomes the controlling rule. The EGC size must be increased to meet the updated overcurrent protection requirements. Consider a circuit with a 100 amp OCT and a 100 amp EGC. If the OCT is upgraded to 150 amps, then the EGC size must also be increased to 150 amps to meet the requirements of 250.122. A 250.122 should always be applied when selecting the minimum size of the EGC based on the OCT rating. If the EGC is then increased for voltage drop considerations, a larger size must still meet the requirements of 250.122. To summarize, the dominant rule depends on whether or not the OCT or circuit current changes. If they remain unchanged, then 250.122 governs the EGC size. However, if the OCT or current increases, then 250.122 takes precedence and the EGC size must be adjusted accordingly. The fundamental principle is ensuring the EGC is adequately sized to handle fault currents as dictated by the overcurrent protection device. If the conductor size is increased solely for voltage drop, but the OCT remains the same, the minimum EGC size does not necessarily need to increase beyond what 250.122 requires. However, it's crucial to verify that the selected EGC is still sufficient for the increased conductor size and the potential fault current it might carry. Voltage drop calculations influence the selection of conductor size to ensure that the voltage at the load remains within acceptable limits, typically not exceeding 3% for branch circuits and 5% for feeders. These calculations involve factors such as the length of the conductor, the current it carries, and the conductor's impedance. Increasing the conductor size reduces voltage drop, improving the performance and efficiency of the electrical system. When upsizing conductors for voltage drop, the initial step is always to determine the minimum EGC size based on the rating of the OCT protecting the circuit, as specified in 250.122. This establishes the baseline for EGC sizing. Then calculate the required conductor size to meet the voltage drop requirements for the specific circuit. If the conductor size needed for voltage drop is larger than the minimum size required for the OCT, the larger conductor size is selected. However, the EGC size must still be evaluated based on the increased conductor size, as outlined in 250.122. It's important to note that the EGC size is based on the OCT rating, not directly on the conductor size chosen for voltage drop, but the installation requirements of 250.122 must always be met. An example would be a 20 amp circuit where voltage drop calculations require a number 10 conductor instead of the number 12 conductor normally used for a 20 amp circuit. In this case, the EGC must still be sized according to the 20 amp OCT, which typically requires a number 12 copper EGC. The fact that a larger number 10 conductor is used for the ungrounded and neutral conductors does not automatically necessitate a larger EGC, provided the number 12 EGC meets the requirements of 250.122 for a 20 amp circuit. If, however, the OCT were to be increased such that the new OCT rating required a larger EGC than the number 12, then the EGC would need to be increased accordingly. Consider a scenario where a 30 amp circuit is initially installed with number 10 conductors and a number 10 EGC as per 250.122. If voltage drop calculations later necessitate increasing the conductor size to number 8, but the oct remains at 30 amps, the EGC can generally remain at number 10, provided it meets all other applicable requirements. The critical factor is that the oct rating has not changed. Now, if the load on the circuit is increased, requiring the oct to be upgraded to 40 amps, 250.122. It dictates that the EGC must also be upgraded to match the requirements for a 40 amp oct, even if the number 8 conductors installed for a voltage drop would technically allow for a larger oct. The overriding principle is that the EGC must always be sized appropriately for the oct protecting the circuit. Firstly, determine the minimum EGC size based on the oct rating according to 250.122. Secondly, perform voltage drop calculations to determine if larger conductors are needed to maintain acceptable voltage levels at the load. Thirdly, if larger conductors are required for voltage drop, ensure that the EGC is still sized appropriately for the oct protecting the circuit. If the oct rating remains unchanged, the EGC size generally does not need to be increased solely due to voltage drop considerations. Fourthly, if the oct rating is increased, the EGC size must be increased to meet the requirements of 250.122 for the new oct rating. Fifthly, consider other factors that may influence EGC sizing, such as equipment grounding requirements and the presence of sensitive electronic equipment. Sixthly, always consult the latest edition of the National Electrical Code (NEC) and local amendments for specific requirements and guidance on EGC sizing. Seventhly, ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local codes. Eighthly, properly document all calculations and decisions related to EGC sizing and voltage drop to ensure compliance and facilitate future maintenance and modifications. Ninthly, when in doubt, it is always best to err on the side of caution and install a larger EGC to ensure adequate grounding and safety. Tenthly, regularly inspect and test the grounding system to verify its effectiveness and identify any potential issues. Proper grounding is essential for electrical safety and helps to protect people and equipment from electrical shock and damage. Increasing conductor size for voltage drop does not automatically necessitate increasing the EGC size if the oct rating remains the same. However, the EGC must always be sized appropriately for the oct protecting the circuit as required by 250.122 of the NEC. Always prioritize safety and consult the relevant codes and standards to ensure compliance. Here is an example of a feeder circuit. Suppose a 200 amp feeder is initially installed with number 3/0 copper conductors and a number 8 copper EGC in accordance with 250.122. Voltage drop calculations indicate that the number 3/0 conductors are inadequate and number 4/0 conductors are required to maintain acceptable voltage levels at the load. Since the oct remains at 200 amps, the EGC can generally remain at number 8 copper, provided it meets all other applicable requirements. However, it's important to verify that the number 8 EGC is still adequate for the increased conductor size and the potential fault current it might carry. Now consider a scenario where the load on the feeder is increased, requiring the oct to be upgraded to 225 amps. In this case, 250.122. It dictates that the EGC must also be upgraded to match the requirements for a 225 amp oct, which would typically require a number 6 copper EGC. This upgrade is necessary even though the number 4/0 conductors installed for voltage drop would technically allow for a larger oct. The key takeaway is that the EGC must always be sized appropriately for the oct protecting the circuit, regardless of the conductor size chosen for voltage drop. The NEC provides tables that correlate oct ratings with minimum EGC sizes. These tables should be consulted to determine the appropriate EGC size for a given oct rating. In addition to the NEC requirements, local codes and regulations may have additional requirements for EGC sizing. It's important to be aware of and comply with all applicable codes and regulations. In some cases, it may be necessary to install a larger EGC than the minimum size required by the NEC or local codes to meet specific equipment grounding requirements or to address concerns about sensitive electronic equipment. For example, sensitive electronic equipment may require a dedicated EGC to minimize noise and interference. In these situations, it's important to consult with a qualified electrical engineer to determine the appropriate EGC size and configuration. Let's explore a scenario with a motor circuit. A 50 horsepower motor is supplied by a 480 volt, 3-phase circuit. The motor's full load current is 65 amps, and it is protected by an 80 amp inverse time circuit breaker. According to 250.122, and table 250.122, the minimum size EGC for an 80 amp oct is number 10 copper. However, voltage drop calculations indicate that the conductors need to be upsized from the code minimum of number 6 copper to number 4 copper to maintain adequate voltage at the motor during startup. Since the oct remains at 80 amps, the EGC can remain at number 10 copper. The increase in conductor size due to voltage drop does not necessitate an increase in the EGC size as long as the oct rating remains unchanged. If the motor is replaced with a larger 75 horsepower motor that has a full load current of 96 amps, the circuit breaker needs to be increased to 110 amps. Now, according to 250.122, and table 250.122, the minimum size EGC for a 110 amp oct is number 8 copper. The EGC needs to be upsized from number 10 copper to number 8 copper to comply with the code, even though the conductors were already upsized to number 4 copper for voltage drop. The key point to remember is that the EGC size is primarily determined by the rating of the oct, not the size of the circuit conductors. While upsizing conductors for voltage drop can improve the overall performance and efficiency of the electrical system, it does not automatically require upsizing the EGC unless the oct rating is also increased. There can be other conditions to consider with the EGC, such as the length of the run, the type of raceway, and whether other equipment requires a larger EGC. It's important to consider all relevant factors when determining the appropriate EGC size.